In topic 6, we extend our discussion on the normal distribution, which started by looking at how population data, can be distributed in this nice even curve, which has special properties that we can utilize. However, often the population data is skewed, for example in real estate examples, and we'd like to make it normally distributed. And other times we don't have the full population data, we only have data that we've sampled. So we need to be able to use these as well. So we're going to look at a technique that, one, can make skewed data normally distributed, make it have a more even distribution, and we're going to look at methods for analysing and visualising data that we've sampled. So not data from an entire population, but from a subset that we've sampled. First of all, download the CEO salaries file, which has the age and salary of the top 60 CEOs in the US in the late 1980s. And if you could calculate the mean and standard deviation of the salaries and ages, and then do a histogram of the full data set, and you'll see that it's somewhat skewed by some CEOs that have extremely high salaries, whereas most have a sort of moderate salary. On this spreadsheet, what I've also done is randomly select 20 CEOs by using a random number table. I've randomly selected 20 CEOs, and I have done a histogram of the salaries of those 20 CEOs. And what you'll see is that histogram is not skewed. It's actually become normal. And this is a property of good random sampling. If we randomly sample within a skewed data set, our data more often than not becomes normal, and we can utilize this fact. The mean of this subset of CEOs that we have sampled, these 20 CEOs, is an estimate of the population mean. You'll see that the mean of those 20 CEOs that I randomly sampled is a little bit different to the mean of all 60. What I've done effectively by sampling those 20 is attempt to estimate the true mean salary. So we're going to look at techniques for doing this, as well as ways of using this sample mean and providing people with a proper estimate of the true mean. So here's an example of what I'm saying in the bottom right here. In the hard black line, we have the population data set, and you can see that it's skewed to the right. Then what's happened is we've randomly sampled within that data set, and the distribution of those random samples is in the grey. And you can see that's a nice even distribution. And what the mean of that nice even distribution doing is estimating the mean of the skewed data set. The standard deviation of this normal distribution is estimated as the standard deviation of the population divided by the square root of the sample size that we have sampled. That's the sample standard deviation, the standard error. Due to a concept known as essential limit theorem, as our sample size increases, our estimate of the true mean becomes more accurate. And this is represented here on this chart. In the x-axis we have the number of observations taken, so the sample size, and in the y-axis we have the estimate of the mean. The true mean in this case is that dashed line at 25, and at the start when we've got a small sample size up to around 10, the mean fluctuates all over the place, but as we get to a sample size of about 50 and beyond, we can see that our sample mean is now quite nicely estimating the true mean, and that's what we're after. When we're estimating the true mean, we can't provide a single spot estimate. We can't just take the average of a sample, get a single number and say, well, this is around about what we think the true mean is. It doesn't provide the reader with enough information. It doesn't tell the reader how confident we are in our estimate. What we do instead is provide an estimate of the true mean with a margin of error attached. So we might say, we believe the true mean is 250 plus or minus 20, and we're 95% confident that that is correct. This is called a confidence interval. The sample mean plus or minus a margin of error. The confidence interval ranges between the lower confidence level and the upper confidence level, also known as the lower confidence limit and the upper confidence limit. The lower confidence limit is the sample mean minus the margin of error. The upper confidence limit is the sample mean plus a margin of error. And we'll see how we calculate this margin of error. To come up with our margin of error, we use a similar concept to the 68, 95, 99.7% rule from the normal distributions, where, for example, 95% of values were 2 standard deviations either side of the mean. Instead, when we're coming up with a confidence interval to estimate the true mean, we say we're 95% confident that the true mean is a certain number of standard deviations either side of our sample mean. And we get the number of standard deviations either side of the mean using these special Z values. These Z values are found from a table, and we'll explore now how we look them up. So this is how it's done. We have the sample mean here represented by an X with a bar on top. And we know we need a confidence interval either side of that mean, which represents a range of values that we are confident that the true mean is found. In the top right distribution there, we're saying our mean is in the middle of that distribution, and a certain number of values either side where a certain level of confidence the true mean is found. Depending on our level of confidence, we multiply the standard error, which is the population standard deviation divided by the square root of the sample size, by a different number we call Z. And we grab Z from standard tables. And here's an excerpt from table C, the bottom of table C, which tells us what a value of Z has to be for a certain level of confidence. So if we want to be 95% confident, we would use a Z value of 1.96. So what we do is we multiply 1.96 times the standard error to get our margin of error. Again, the standard error is the population standard deviation divided by the square root of the sample size. So we have our sample mean plus or minus Z times the standard deviation divided by the square root of the sample size. Let's look at an example now. We wish to estimate the true mean weight of an egg, of a brown egg. So we randomly sample 12 brown eggs by getting a random carton of eggs. And within this random carton of eggs, which contains 12 eggs, the average weight of an egg is 62.4 grams. So we have a sample mean, and this sample mean is an estimate of the true mean. We know, or we're given, that the standard deviation of all egg weights is 5 grams. So the population standard deviation is 5 grams. We want a 95% confidence interval for the true mean weight of a brown egg. So we do this by coming up with a lower confidence limit and an upper confidence limit, which gives us our confidence interval, or the sample mean plus or minus a margin of error, where the margin of error is calculated as Z times the population standard deviation divided by the square root of the sample size. We're given the sample mean, 62.4, and we're given the population standard deviation, 5. We know what the sample size is, it's 12. So all we're looking for now is the value of Z. So we go to that table. We're looking for 95% confidence, so we would use the value of Z, which aligns with 95% confidence, which is 1.96. So we substitute those numbers into that equation, and that will give us the margin of error that we need to come up with our confidence interval, which will estimate the true mean with 95% confidence. So here are the calculations here, all those numbers subbed in, and we can see once we sub all those numbers in, our confidence interval for estimating the true mean with 95% confidence is 64.2 plus or minus 2.8. Therefore, we would say we are 95% confident that the true mean weight of all brown eggs lies between 61.4 and 67 grams. We're not saying that all brown eggs or 95% of brown eggs will be between those values. We're saying the true mean weight is somewhere between those two. If we wanted to provide a confidence interval where we're 99% confident, we'd get the value of Z, which aligns with 99% confidence. And that's just a bit over 2. You can see that on the table. And that will expand our confidence interval, which makes sense. Because if we want to be more confident, we need to provide a larger range that we believe the true mean is in. In this second example, we're looking at a test conducted in the US. The NAEP, National Assessment of Educational Progress, which is a short test to see where students are at, where people are at. Test scores can range from 0 to 500, with a higher score meaning they've done better. All tests undertaken, all the scores that have been produced by when undertaking this test have a standard deviation of 60. So our population standard deviation is 60. We want to know what the mean score is. To work out what the mean score is, we take a random sample of 840 participants and get a sample mean from that. And we find that the sample mean, based on the scores of these 840 randomly selected people, is 272. So now we have a population standard deviation, we have a sample mean, and we have a sample size, and we want to provide a confidence interval for the true mean score based on this sample. So we'd use the same equation as before. The sample mean plus or minus a margin of error. The margin of error being a value of Z times the population standard deviation divided by the square root of the sample size. We have the sample mean. We have the population standard deviation. We have a sample size, 840. We just need a value of Z. Now in this example here, we're not provided with a confidence level on this slide. So let's say we wanted to be 95% confident. Then Z again would be 1.96. Often in studies we want to know what our sample size needs to be such that we can achieve a certain margin of error. For example, we may be legally required to have a certain margin of error in our estimate of the true mean. So to calculate the standard deviation we need for a certain margin of error based on a known population standard deviation, we just rearrange the equation which calculates the margin of error, Z times the standard deviation divided by the square root of the sample size. So we rearrange it just as shown on this slide here. We substitute the numbers in that we know, and that will give us the sample size. And the next slide has an example of that.